So could you please tell us about who you are?
Sure. My name is Daniel Quinn. I'm an assistant professor in the Mechanical and Aerospace Engineering Department at the University of Virginia. And I'm part of the Link Lab, which is a multidisciplinary engineering lab space. And as part of that, I also have a secondary appointment in electrical and computer engineering.
And why did you want to become an aerospace engineer?
I knew I wanted to do something with flying from a young age. I was really into space. Actually, my first plan was to major in astrophysics. So I joined the College of Arts and Sciences. I started taking physics classes, but I found that I missed a little bit of the design and application. So then I switched back to engineering, and right away I knew which engineering I wanted to do. It was aerospace. So that's how I ended up in aerospace engineering.
And one of your research interests is in fluid structure interaction. So could you talk about some of your work in studying these interactions and what is the importance in aerospace engineering?
Sure. So as I started taking aerospace classes, one of the main ones is fluid dynamics. And I found myself really enjoying that topic. There was a lot of calculus, which I like, but it was also a very visual field. We learned about, flow and flow over objects and vector fields and vorticity, rotation in the flow. So it was a combination of a very artistic and visual topic, but also one that had a lot of calculus in it. So I really enjoyed that. And then I'd say a subset of fluid dynamics is fluid structure interaction, where you take solids that maybe have some elasticity to them, they can bend, and then you put them in a fluid, and then you think about how those two, the dynamics of those two will affect each other. So the fluid affects the solid, and the solid then affects the fluid, and you think about that coupling. And the reason that's important for aerospace is a lot of times you have some, a plane is a solid embedded in a fluid. So as the plane moves through this fluid of air, if there's any flexibility, so say the wing, any solid object has a little bit of flexibility. So the wing may be able to bend a little bit. And so aeroelastic flutter is a classic fluid structure interaction problem. So you've got the air coming over the wing is a little bit flexible, and it starts to vibrate. And you've got to factor those vibrations into the design of the airplane, or you'll have serious problems. So fluid structure interaction theory comes up a lot in aerospace design.
Your research expertise also covers biomechanics and bio-inspired robotics. So could you tell us about some of the bio-inspired robot concepts that you've been working on and its possible future use in aerospace engineering?
Sure. So as I got farther in my undergrad degree, aerospace, I started to get involved in this research project that was looking at bio-inspired engineering. And we were actually looking at fish. So, even though aerospace people think of in the air, a lot of those same equations apply to different fluids like water. So underwater propulsion uses a lot of the same math as aeronautical flying through the air. So we were working on this fish robot project, and then I got involved in that in graduate school and really got hooked on that topic. So we look to fish and we see how they swim, and then we think about what are ways that we could design robots that swim more like fish. And it's not just underwater, like I said, similar math in the air. So after grad school, I went on to another lab where they were studying birds and how birds flew, and how could we design robots that fly more like birds. So the reason this is a topic that people study is more than just it looks cool, though it is cool to have a robot that swims like a fish or flies like a bird. But there are also a lot of practical reasons why you'd want to do this. Our current technology is pretty loud. It's really all propeller driven, so it makes a lot of noise. And it's designed for specific cruise speeds. Propellers are notorious for having they call it a specific advance ratio. It's the ratio of how fast it's spinning to how fast it's moving. It's designed for one advance ratio. So Fish and birds, though, are much more multimodal. They can swim and fly very slowly, or swim and fly very fast. They can turn, they change speeds all the time. They're very maneuverable. And they're also much, much quieter than propeller technology. So those are the main two reasons people are excited about using fish and birds to inspire future vehicles, is that we could potentially make them a lot quieter and a lot more maneuverable and a lot more efficient as they're maneuvering.
Mhm. And I also read that you created a robotic tuna fish. So why would you have created a robotic tuna fish?
Yeah, so I went to this lab studying birds, but now that I started as an assistant professor, I'm back in the fish world. So we're looking at robotic fish. And one of our most recent projects, we were looking at a tuna and trying to build a robot that swims more like a tuna. And for all the reasons I just mentioned, a robot like that could be more maneuverable, more efficient, more quieter. So you could use it for, ocean exploration, or maybe you have hundreds of these things doing climate mapping or terrain mapping or a search and rescue mission. And for all those kinds of missions, you want something that is more maneuverable and efficient over a range of speeds. But that's kind of fish in general. The reason we picked tuna is tuna are really fast. They're really fast. They're serious predators in the ocean. They're a really formidable species. So a lot of people think they're a good model organism to think about how could we design a really effective swimmer. So that's why we chose tuna. As, they swim over a range of speeds. They're really fast. They're apex predators. They're really impressive swimmers. So that's why we chose them.
And what were some of the challenges associated with creating it?
One thing that's actually surprisingly difficult is knowing how flexible you should make a fish-like robot. And it sounds easy, why don't we just make it as flexible as a fish? But that's actually a pretty hard thing to know, how flexible a tuna is, because of tuna's flexibility, they change their flexibility by tensing their muscles. So we can't just take a dead tuna and measure its flexibility. It wouldn't mean anything, because it derives its flexibility from the tensing of its muscles. And we can't really just measure how flexible a tuna is while it's swimming, because all the tests we would do to test something, how stiff it is, pull on it or have it droop over the edge of a table, none of that makes sense for a fish while it's swimming. So that simple question, how flexible are tuna, actually is something that biologists don't really know. And that makes it a challenge for engineers like me to build a robotic model of a tuna, because we don't know how flexible it should be. So that was actually a big part of the research we've been doing, is studying how flexible to make it. And in particular, if there's not one best flexibility, how can we make a design that can change its flexibility like tuna do? Because tuna, they can tense their muscles to change their flexibility while they're swimming. So our most recent project, we designed a fish that had a little artificial tendon, and it could tense its tendon and control its own flexibility.
And you also do research on energy harvesting. What are some of the energy harvesting concepts that you've been working on or have worked on?
So energy harvesting sounds like a pretty different topic, but actually it's pretty related, or it's not pretty related, but I mean, it's a close cousin. And the reason is that with fish and birds, you're talking about some structure that's putting energy into the fluid. So it's probably some flexible structure that's putting energy into the fluid. If you run all those equations in reverse and you think about the fluid putting energy into something that's moving, and you flip the direction of the energy flow, now you're talking about an energy harvester, something that's designed to extract energy from the flow instead of put it in. So a lot of the same equations apply. And again, they work in air and water. So you could talk about energy harvesting in air or energy harvesting in water. One topic we're looking at specifically is piezoelectric harvesting. So piezoelectric is a material that generates a voltage when it bends. So if you put that in a fluid, say air or water or blood or whatever, then as the fluid moves back and forth, the piezoelectric is going to bend or maybe flutter in one direction, and all that bending is going to generate energy that you can use. So we are looking at how you could design small sensors that could harvest their own energy. Two places you might want to use this is maybe you want a whole bunch of sensors in the air conditioning system in a building this is a popular topic these days, is how can you make air conditioning systems more efficient? Because that's huge energy costs in the world, is running these systems. So if you could make them smarter by having sensors distributed through the network to decide when should I open this vent, how high, how fast should this pump be running, and maybe that all depends on where people are in the building, certain temperatures. You want a lot of sensors, but you don't really want to wire up the entire building. So it would be great if you could have a batteryless solution, something that's actually borrowing energy from its surroundings. And in an AC system, you've got air flowing around. So you could almost think of it as a tiny little wind turbine that's harnessing the energy of the air, using that to sense, and that way it's generating its own electricity. The other place we're trying to think about, could you do that, is in a human airway. The batteryless solutions are big in implantables. People are trying to design implantable sensors in the body, but you don't want to have bulky batteries. You don't want to recharge. You certainly don't want to have wires sticking out of the skin. So the best solution often is to generate your own electricity from within the body. So it's batteryless. So we're looking at fluid flows in the body, blood, urine, air, and thinking, hey, could we design a sensor that actually harnesses the energy from that fluid? And that way you wouldn't have to recharge it.
Mm-hmm.
So those are the two energy harvesting topics we're considering.
Mm-hmm. And what are cyber physical systems, and how are these systems utilized in creating a machine or like an aerospace vehicle?
So I started by saying I work in the Link Lab, and our specialty here is cyber physical systems. And those are systems that have physical components, but also cyber components. And they have to work together to make the system work. Sometimes people use the idea of the Internet of Things as they're talking about cyber physical systems. Sometimes they'll even use those terms interchangeably. It's this idea that if you have a device, a physical device, but something that has smart software on there and potentially maybe network with other devices, then you can build this system that can do amazing things that you couldn't do with just a physical device, and you couldn't do with just a software network. So for the example of aerospace, one example could be a small unmanned vehicle, say a quadrotor. Some people call these little drones. There's a lot of research on how can you fly one drone more stably. There's just starting to be more research about how could you have a whole swarm of drones. So a swarm of drones would have to be a cyber physical system, because for them to operate, they need to understand their own physics, the physicality of each device, but they need to be networked and using some smart algorithm so that they all coordinate. So you've probably seen these light shows where you've got swarms of drones working together. People dream of futures where swarms of drones can lift things and move them around, or do coordinated search and rescue missions. And those are examples of cyber physical systems, a swarm of unmanned vehicles. And I think part of what makes that so interesting to me, that particular cyber physical system, is that there's a lot of aerospace engineering in there. There's a lot of fluid dynamics in there. We have to understand how the air is moving around one quadrotor, and then how the air is moving around a swarm of quadrotors, and somehow build that into the control algorithms in a way that it becomes a smart system.
And what would you say has been your toughest accomplishment so far?
In my career, you mean?
Yes.
I think probably getting my PhD. was a lot of work. That graduate school, in particular, passing the qualifying exams. At my school, they call them general exams, but they're all kind of similar, where you study and you study and you study for months, and then you take this oral exam where professors really make sure that you've learned all this material. And I would say a lot of the things I know about fluid dynamics, I learned in those few months, just really, challenging myself to learn everything I could for that test. And it was challenging. I might say the biggest challenge so far.
Mhm. And what is a big milestone that you're looking forward to in your research?
I think we're getting close to the place where fish-like robots could be massively deployable, in a commercial sense, that people could buy, that you could have a platform that's standard enough that people could have a fish-like robot that you could buy off the shelf, essentially. And once we get to that level, I think their uses will really start to be more conceivable in a mainstream sense. People will start to see what you could use this for, and it'll also be more fun because we could do undergraduate classes where we buy a bunch of these things and have them, compete to write the best control algorithm and have them racing these fish robots through swimming pools. And I think we're just a few years away from getting there, and I think it'll build a lot of excitement that we can right now feel in the research world, but you can't really see it yet in the public sphere because they're not quite that mass producible yet.
And to high schoolers like me and to younger generations that want to become aerospace engineers, what would be your advice to be successful in this career?
I think my advice would be, this is not so specific to aerospace, but I think this is the advice I'd give for aerospace, but it applies to a lot of different things, which is to ask questions if you're confused. I think it's really tempting, and it's tempting for me too, when someone's explaining something, whether it's in a one-on-one session or a class or a group of people, it's really tempting to nod along, even if you don't quite see what they're saying, because we all feel that social pressure we want people to think we're smart. So we nod along thinking that will make us appear smarter. But by asking questions and telling people that we are lost or we're confused, that's how we get smarter. So ironically, by trying to stop people from thinking that we're not smart, we're actually preventing ourselves from getting smarter. And I think that's a mistake that we all make. As a specific example, when I was a grad student, there's this senior professor, the chair of the department. Everyone really respected this person. And he would always just raise his hand in seminars and say, I'm lost. I have no idea what you're talking about. I'm really confused. He was just really confident in his, he wouldn't shy away from the fact that he was lost. And I think people really respected that because it made him so much smarter. This willingness to make yourself vulnerable and say, hey, I don't understand what you're saying. And I think that's a really important skill in any field, but especially in engineering, where you're designing these complex systems, and if you're just nodding along, it's going to be really damaging to your intellectual growth. So that would be my advice. Don't nod along, ask questions.
Well, I thank you for joining me, and thank you for letting me interview you. I think that was great.
Great. Yeah. Thanks so much for having me. This has been fun. Let me know if you have any follow-up questions.
Mhm.